Okay, welcome everyone to today's lecture. So today we'll be talking about the determinants of a square matrix. So before we get into the lecture, let's start with some notation. Okay, so um, let A be a square matrix, an n by n matrix. Determinant A is denoted as that of A. Okay. So first of all, the determinant of any square matrix is a number. Okay, so first of all, it is a number, and that number will tell us some information about that matrix. Okay, the determinant of any square matrix will tell us some information about the matrix. That's why people would be interested in this number. Okay, so first of all, let's start with the easiest square matrix, a 2 by 2 matrix. Okay, so we will have the determinant of 2 by 2 matrices. Okay, so suppose I'm having a 2 by 2 matrix in the form of A, B, C, D like this. Then the determinant of this matrix is defined to be the subtraction between AD and BC. So the determinant of this square matrix is AD minus BC. Okay, so this is the definition of the determinant of a 2 by 2 matrices. Okay, so it is pretty easy to follow, right? Let's have some example over here. So suppose A in this case is the square matrix 2, 4, -1, 6 like this one. So according to the definition, in order to calculate the determinant of this matrix, we will need to take the product of the two entries on the main diagonal and subtract the product of the other two entries on the other diagonal. Okay, so we should have 2 multiply 6 minus -1 multiply 4. Okay, so 2 multiply 6 is actually 12. -1 multiply 4 is -4. So 12 minus -4 is 12 plus 4. So the answer should be 16. Right? Okay, let's move on to the determinants of square matrix, but with bigger size. So as you can see, when the size of the square matrix increase, the number of the entries in the matrix also increase. Like in a 2 by 2 matrices, we will have 4 entries, but in a 3 by 3 matrices, we will have like 9 entries in total. So it is impossible to form a general formulation to determine the determinant of the matrix in terms of all the entries in the matrix, right? It is impossible. Like for example, if we are trying to find a determinant of a 4 by 4 matrix, then there would be like 16 entries. Okay, so it is impossible to remember the formula. So instead, people will try to construct a formula using the determinant of matrices of smaller size to construct the formula for the determinant of matrices with bigger size. Okay, so in order to do that, first we will talk about a concept of the ij minor of a matrix. Okay, so let's talk about the ij minor of a matrix. So what is the ij minor of a matrix? Okay, so let A be a 3 by 3 matrix. The ij minor of A, which we will denote as notice as a It is exactly the determinant of the 2x2 matrix received through deleting the I row and the J column. Okay, so an example over here. So for example, here A is a 3x3 matrix in the form of like 1, 2, 3 on the first row, 4, 3, 2 on the second row, and 3, 2, 1 on the last row. Okay, so let's try to calculate the minor of A11 and minor of A22. Okay. Oh, and also I forgot to mention about another notation of the determinant of matrix. So instead you are using this notation of det A, you can also put the matrix between two vertical lines, like this one. You can also use this notation to denote the determinant of A. This is also another notation of the determinant of square matrix. Simply put the matrix inside two vertical lines. Okay, so the formula is still the same. So sometimes I will use this notation, that of A, but sometimes I will use this notation. Okay, so here, according to the definition, in order to determine the value of the minor Aij, first of all, you start with the matrix A, and then you delete the I row and the J column, right? So for example, here I'm trying to calculate the minor A11. So I'm gonna delete the first row and I'm gonna delete the second row. So this 2x2 square matrix is the remaining matrix after I have deleted the first row and the first column. So the minor A11 is actually the determinant of that matrix. So here we got minor A11 is actually the determinant of the matrix 3, 2, 2, 1. And also according to the definition of the determinant of 2x2 matrices, here in order to calculate this, we will have 3 multiply 1 minus 2 multiply 2. So the answer should be negative. Right? Next, we will talk about the minor of A32. A32. So similarly, now I'm going to delete the third row and the second column. Okay, so what we will have now will be the matrix 1, 3, and 4, 2. So the determinant of this matrix should be 1 multiplied 2 minus 4 multiplied, so 2 minus 12. So the answer should be negative. This is how we determine the Ij minor of a matrix. Okay, it's pretty simple, right? Okay. So after we have talked about the Ij minor of a matrix, next we will set up another definition, which is the Ij cofactor of a matrix. Okay. So Ij cofactor. Okay. So the Ij cofactor of 3x3 matrix A, which will be denoted as cofactor COL A and J. Okay, so the formula for a cofactor is pretty easy. So the cofactor the ij cofactor of A is actually equal to the minor Aij, but we will multiply this number with -1 to the power of I plus j. Okay, so as you can see, the minor, the ij minor of a matrix is already a number. So because you are multiplying that number with another number, so the cofactor, the ij cofactor of a matrix is also a number. Okay, so in this case, for example, if I want to, using the same example over here, if I want to construct the cofactor A11 and the cofactor A32, simply I'm going to use this formula over here, right? So the cofactor A11 should be equal to -1 to the power of 1 plus 1 multiplied by the minor A11. On the other hand, the cofactor A32 should be equal to -1 to the power of 3 plus 2 multiplied by the minor of A32. And we have already calculated the minor A11 and the minor A32 over here. Okay, so let's put these numbers together. So -1 to the power of 2 is 1. Okay, and the minor of A11 is -1. So the cofactor A11 is -1. Why -1 to the power of 5 is actually -1. -1 multiplied by -10. So the answer should be 10. Okay. So after we have defined what is the ij minor and the ij cofactor of a square of any 2 by 2 square matrix, we are now officially able to construct the formula for the determinant of any 3 by 3 matrix. Okay. Okay, let's erase this. So determinant of a 3 by 3 matrix. Okay, so start with a 3 by 3 matrix. Let A be a 3 by 3. Okay. Then the determinant of A is calculated. Okay, so in order to calculate the determinant of a 3 by 3 matrix A, first we will pick a row or a column. Oh, I forgot to mention that here, the cofactor Aij, oh, I'm sorry, I'm using the wrong notation. The cofactor Aij, sometimes we will say that it is the cofactor correspond to the entry Aij in the matrix. Okay, so the cofactor Aij will be considered as the cofactor correspond to the Aij entry in the matrix. Okay, so get back to this definition over here. Pick a row or a column, then okay, next we're gonna find the product of the entry and their corresponding cofactor. Okay, so the entries are number and the cofactors are also number. So we can absolutely will be able to find the product of those two numbers. Okay, after you have found the product of each of the entry and its corresponding cofactor, then we are going to take the sum. Okay, take the sum. Okay, so take the sum of those numbers. Okay, let's say that when you take the sum of those numbers, the determinant of A is actually defined to be that sum. Okay, so let me remind you about the process. First, you need to pick a row or a column. Then you will multiply each of the entry in the row or that column with its respective corresponding cofactor. Then finally, you will take the sum of those numbers and you will get the number which will be defined as the determinant of A. Okay, so like for example, if I'm choosing the I row, if I am choosing the I row, pick the I row. So here, because we are in a 3x3 matrix, so in the I row, we will have entries like AI1, AI2, and AI3, right? This should be the I row of the that's 3x3 matrix. So in this case, the determinant of A should be equals to, first I'm going to take I1 and I'm going to multiply with its corresponding cofactor, which is cofactor big A I1. The same things happen for the remaining two entries. Right? And then I take the sum of all of those products, and that will be the determinant of A. Okay, so because in this case, I am picking the I row, then this formula over here is called the expansion along the I row. Okay, this is called expansion along the I row. If we choose column, then the formula will be called expansion along the I column. Okay. And this expansion over here generally will be called as Laplace expansion or cofactor expansion. Okay, this expansion generally will be called Laplace expansion or cofactor expansion. So this is the name of the formula, okay? Laplace or cofactor expansion. Right? Okay, so let's use the same example over here. And we should try to calculate the determinant of this matrix A based on the definition, okay? So once again, A is 4, 1, 2, 3, 4, 3. 3, 2, 1. Okay. So before we start calculating the determinant of that matrix A, let me explain a little bit about this formula over here. So in this formula, you can pick any row or column, and the row or the column you pick will not change the final result of the determinant. So maybe some of you will choose the first row, some of you will choose the bottom row. It doesn't matter. the determinant of that matrix is a constant and it should stay the same no matter what row or column that you pick. Okay, so normally I would pick the first row or the first column because it is the easiest thing that we can think of, right? Okay, so if you are trying to calculate the determinant of this matrix, first of all, I am choosing the first row. Okay, so the first entry is 1. Right? The second entry is 2. And the third entry is 3. Okay, so I am multiplying these 3 entries with their corresponding cofactor. So what is the cofactor? Cofactor is -1 to the power of I plus j and multiply that by the minor aij. Okay, so this is A11, right? This is A11. So I am multiplying that with -1 to the power of 1 plus 1. And then followed by the minor, which is the determinant of the 2 by 2 matrix after we have deleted the first row and the first column. So delete the first column, delete the first row, you should have 3, 2, 2, 1. Right? 3, 2, 2. Similarly, for the second entry, this is lying on the first row and the second column. So it should be 1, 2. Right? I'm going to multiply this with -1 to the power of 1 plus 2. And the minor, the corresponding minor should be the determinant of the matrix 4, 2, 3, 1. Right? 4, 2, 3, 1. Last but not least, for the final entry, it is lying on the first row, the third column. So we should multiply this with -1 to the power of 1 plus 3. And then multiply with the determinant of the matrix 4, 3, 3, 2. 4, 3, 3, 2. Okay, and I'm gonna add all of these numbers together. Okay, that is the definition of the determinant according to the definition. Okay, so here -1 to the power of 2 is 1, -1 to the power of 4 is 1, -1 to the power of 3 is -1. So we should have 1 multiply something, the determinant of this, -2 multiply the determinant of this, and then +3 multiply the determinant of this. Okay, let's calculate the determinant of these 2 by 2 matrices. So we should have 3 minus 4, right? 3 minus 4. So the answer should be -1. Right? 4 minus 6. 4 minus 6. So it should be -2. Last but not least, 8 minus 9. 8 minus 9. So the answer should be -1. Okay, so here we got -1, we got 4, we got -3, right? -1, 4, -3. So the answer should be 0. Okay. So that is the determinant of this 3 by 3 matrix. Okay, so many of you can choose another way to calculate this determinant. You can pick the first column, the second column, whatever column or row you want, but the determinant would still be the same, would still be 0. Okay, so yeah, so we have finished defining the way to determine the determinant of any 3 by 3 matrix, and actually this definition can be extended to any square matrices. So instead of any 3 by 3 matrix, you simply gonna replace the definition with any n by n matrix, right? Also the aij minor and the cofactor aij cofactor, you simply replace that by with any n by n matrix, and this is the general formula to find the determinant of any n by n matrix. Okay, so as you can see, in order to calculate the determinant of a 3 by 3 matrix, you need to know how to find a determinant of a 2 by 2 matrix, right? So similarly, if you want to find a determinant of any 4 by 4 matrix, then you should be able to find the determinant of the 3 by 3 matrix. Okay, so that's the definition of a determinant. So let's use a formal definition for the determinant of n by n matrix. Okay. Determinant let A be an n by n matrix. Okay, and suppose the determinant of a minus 1, a minus 1 matrices will be defined. Okay, then the determinant of matrix A is actually equal to the sum of Aij multiplied with its cofactor Aij. So as you can see here, we can expand along a row or a column. So we will have two formula for that definition over there. If you take the sum from j equals 1 to n, we are fixing the I, right? We are fixing the I, and I stands for the row. So actually this formula is expansion along the I row. Why if you use the same formula, but you are fixing the j index and you let I run from 1 to n, here the column is fixed. So you are expanding along the j column. Okay, the formula is still the same as this one, but with a more general formula. Okay, and so that is the determinant of any n by n matrix. Okay, so let's talk about how to find the determinant of a very special matrix, which is the triangular matrix. Okay, let's talk about the determinant of a triangular matrix. Determinant of triangular. Okay, so suppose here I am having a 3 by 3 matrix A in the form of triangular matrix where the entry is 1, 0.1, 0.0.5, 0, 2, 7, and 0, 0. And we will try to find a determinant of this matrix based on a definition. Okay, so based on a definition, you will need to pick a row or a column and then expanding along that row or column, right? So a wise choice in this example here, I will choose the first column. Why? Because as you can see in the first column, only the first entry is a non-zero entry. All the other entries are 0. And when you multiply the 0 entry with its cofactor, it is still 0, right? When you multiply 0 with any number, the result would be 0. So we don't need to care about the cofactor of this entry anymore because 0 multiplied anything is 0. So when you try to find the determinant of this one, you will only need to choose the first entry, which is 1, multiply that with its cofactor, right? So the cofactor of this one should be -1 to the power of 1 plus 1, and then multiply the determinant of this 2 by 2 square matrix. So 2, 7, 0, 3. So -1 to the power of 1 plus 1 is actually 1. Ignore that. And here, this determinant of this matrix is 2 multiply 3. Minus 0 multiply 7. So 0 multiply 7 is 0. Okay? So actually, it should be 1 multiply 2 multiply 3. Right? And as you can see, 1, 2, 3 are actually the entry that are on the main diagonal. Right? So basically, triangular matrices are a very special type of matrices that we can easily find the determinant of those matrices simply by multiply all the entries on the main diagonal. Okay, so that is the definition of determinant of triangular matrix. Okay.
Third size is greater than 3 by 3, or
What?
you said determinant, is that just for 3 by 3?
No, it is applicable to any
Okay.
size of the square matrix. Okay, I am writing that now.
Oh.
Okay, so if A is, if A is okay, so this is applied to any type of triangular matrix, including the upper triangular matrix and the lower triangular matrix. Okay, so the upper triangular matrix are the triangular matrix such that all the entries below the main diagonal are 0, and the lower is opposite to that. Okay, so if A is any triangular matrix, then that A is actually equals to the product of all entries on the main diagonal. What is the main diagonal? And this is applied to any size of triangular matrix. So if A is an n by n triangular matrix. Okay, this is applied to any square triangular square matrices. Okay. Okay, so the final parts of today's lecture, we will talk about some properties of determinant that would be really helpful to calculate the determinant of matrices. Okay, so let's talk about properties. Okay, so there are several properties and we will talk about those. Okay, so let's talk about the determinant of the two matrices such that the second matrix is received by applying some kind of row operation to the first matrix. Okay, so let A be an n by n matrix and B be the matrix received by okay, so there are three row operation in total, right? There are 3 operations in total. So we are actually having 3 property over here. Okay, so the first row operation, I just switch the rows in that matrix. Okay, so switching 2 rows of A. So if the new matrix is received by switching 2 rows of the original matrix, then their determinant are opposite of each other. That of B should be negative, that of A. Okay. And the second type of row operation is to multiply a row with a scalar. Okay. Multiplying a row A with the scalar. Okay, so let me highlight this. You are only multiplying a row with the scalar K. So in this case, the determinant of B is actually equal to K times the determinant of the original matrix. Okay, so this property is only about multiplying a row with a scalar K. So if you are multiplying more rows with more scalar, then the answer should be the product of all these scalar multiplied by the determinant of the original matrix. Okay, if you are multiplying each row with different scalar, then the new matrix, the determinant of that matrix, should be equal to the product of all scalar multiplied by the determinant of the original matrix. Okay, so that should be the case for the second property. And last but not least, the third row operation is to add a multiple of any row to another row. So the third type of operation is the easiest one to remember. In this case, the determinant of those matrices stay the same. So determinant of B is equal to the determinant of. Okay. Okay, so we are not going to prove these property, but instead we will try to use this property in some kind of example to see how it works, right? Let's talk about it. Example. Okay, so we are sticking with 2 by 2 matrices to make it easy. Not for any specific reason, but just to make it easy. Okay, so here I am having a 2 by 2 matrix A, which is 1, 2, 3. Okay, and I am going to apply 3 different types of row operation in the matrix A to receive 3 different answer matrix B. Okay, so for the matrix B1, I am going to switch the first and the second row to the 3, 4, 1, 2. Right? For the matrix B2, I am going to multiply the first row with the scalar 5. So 5, 10, 3, 4. And for the matrix B3, I also multiplying the first row with 5, and I'm gonna add that to the second row. Okay, so 1 multiply 5 is 5, and 2, 3, we should have 8. 2 multiply 5 is 10, and 2, 4, we should have 14. So 1, 2. Okay, So let's try to use the definition to calculate the determinant of all of these matrices. And let's try to check whether these properties are correct. Okay, obviously it is correct. We're not going to prove that anyway, but let's check. Okay, so the determinant of the matrix A is 4 minus 6. 4 minus 6. So this should be -2. Right? While B1, the determinant should be 6 minus 4. So the determinant of B1 should be 2. Okay, so according to the property, because B1, we are switching two rows of A. So the determinant of B1 should be the opposite, the determinant of A, right? Next, B2. Determinant of B2 should be 20 minus 30, right? So the answer should be -10. And this -10 over there is actually the original -2, but multiplied with 5, right? And the last example, the determinant of B3, we have 14 minus 16. The answer is still -6. So if you are applying the third type of row operation, the determinant stays the same. Okay, so that is the determinant of matrices using row operation. Okay, so next, let's talk about the determinant of a product of two matrices. Let's talk about the determinant of the product of two matrices. And again, we are not going to prove any of these formula, even though you can actually prove those. So if any of you are interested in the proof of this property, you can go to the textbook and check section 3.1.5. All the proofs are stated there. Okay, so let's call this property number 1. Next, we've got the property number 2. Okay, next we've got a property of number 2. So let A and B be n by n matrices. Then, okay, so because A and B are both n by n matrices, then we can actually perform the multiplication of A and B. And people have been able to show that the determinant of the product AB is actually equal to the determinant of A multiplied the determinant of B. Oh, this property is pretty useful, especially when you want to show or to prove some like some theorem or some corollary about the determinant of the multiple or the product of many matrices together. This property here is really useful. Okay. So, and once again, we are not going to prove this. So, yeah. And then we should go with property number 3, which is about the determinant of the transpose of the matrix. Okay, so here, let A be an n by n matrix. And we should have the determinant of A transpose is actually equal to the determinant of A. Okay, so because A is an n by n matrix, then A transpose should also be an n by n matrix too. And the answer, the reason why the determinant of these two matrices are equal is, okay, so let's imagine when you are taking the transpose of any matrix, simply you are switching the row of the original matrix and you rewrite that as the column of the new matrix, right? So, and also from a definition, when you are trying to find a determinant of matrices, you can expand along any row or any column. So actually we are using the same formula for these two determinants, but for the original matrix, for example, if you are expanding along a row, then in the transpose matrix, you are expanding along a column and vice versa. Okay, so this formula is the most obvious thing that we can prove. And the final property of determinant that we should talk about is the determinant of the inverse. Okay. And this property is probably the most important property of the determinant. Okay, let A be an n by n matrix. Okay, then A is invertible if and only if the determinant of A is non-zero. So at the beginning of the lecture, I have already introduced to you that the determinant of any matrix is a very special number that tells us some information about the matrix itself, right? So one of the most important information that the determinant will be able to tell us is whether the matrix itself is invertible or not. According to this theorem, any square matrix is invertible if and only if its determinant is non-zero, right? So from now on, if you want to check whether a square matrix is invertible or not, you simply need to calculate a determinant and compare it to zero only. If it is zero, then the answer is no, not invertible. But if the determinant is non-zero, then the answer is yes, the matrix is invertible. So in this case, if this is true, then there would be, so if A is invertible, you would be able to construct the inverse of A to the power of -1. And in that case, there will be some relationship between the determinant of A inverse and the determinant of A. So if this is true, the determinant of A inverse is actually equals to 1 over determinant of A. So simply saying that the determinant of these matrices are inverse of each other. Okay, this is a number, this is also a number. The first number is equal to 1 over the second number, meaning that the determinant of these matrices are inverses of each other. Okay, and actually the second property is actually pretty easy to prove because according to the property number 2, if A is invertible, then the product of A and A inverse is actually the identity. Okay, the product of A and A inverse is actually the identity. So the product over here should be the identity, right? And you should also see that the identity is a triangular matrix and all the entries on the main diagonal are 1. So according to the determinant of triangular matrix definition, the determinant of the identity is actually 1. Okay, so in this case, 1 should be equals to the determinant of A multiplied by the determinant of A inverse. And from that property, you will have this statement over here. Okay, it is pretty easy to prove if you've got the property 2 available. Yeah. Yeah, so I think that's it for today's lecture. In tomorrow's lecture, we will talk about how would we use the definition of determinant of triangular matrix combined with all of these property to like find the determinant of any general matrix in a very simple way. Okay, we will talk about that tomorrow. And also for the second part of tomorrow's lecture, we will also talk about how to find the inverse of the matrix, how to actually find the A inverse matrix when you already know the determinant of the original matrix and the matrix A itself. Okay, we will talk about that tomorrow.